Okay, let me start. Today we're going to talk about the orthogonal projection. So in this week, we will talk about what is the orthogonal projection. So then how can this kind of the orthogonal projection is related to the least squared solution. So before starting, let's recap the last week's lecture. So in lecture 9.1, we were talked about the inner product, right? So inner product, the definition of the inner product is something like this, right? So if we have the vector u and vector v in Rn space, so inner product can be computed something like this, right? So this is the kind of the inner product. So this inner product is has some kind of the desirable properties such as the this one and this one, and this one, right? So you can easily prove this property because the inner product can be formulated with the transpose of the vector, right? So it means that inner product v is equal to u transpose v, right? So it means by using the property of the matrix or the vector transpose, we can easily derive this kind of the property, right? So, and then by using the properties P and C here, we can derive another very useful relationship between left hand side and right hand side, right? So I'm not sure you derive this formulation yourself, but if you are not, please try to derive this one, right? And what was the length of the vector? The length is defined something like this, right? So length of the vector v is the scale root of the vector v in the product vector v, right? And then here is the example. And what was the unit vector? Unit vector is the vector that has the length 1, right? So by normalizing the arbitrary vector with their length, we can make a unit vector, right? So here's the example, right? So what was the distance between two vectors? We can define the distance of the vector u and vector v as a length of the u minus v, right? So here, right? So and then in lecture 9.1, we introduced the orthogonal vectors, right? So what is the orthogonal vectors? What's that? So, okay, as you can see here, if there is a two vector u and v, and if those kinds of two vectors are perpendicular, like this one, these two vectors are called the orthogonal vector, right? So as you can see here, this green line, this one and this one has the same length in case that this vector u and vector v are orthogonal, right? Then we can derive the new formulation. So distance of the vector u and minus vector v, and distance of the vector u and vector v is something like this. These two kinds of vectors should be these two kinds of the length should be same. So finally we can derive this one. So vector u inner product vector v is going to be equal to 0, right? So in other words, the vector v and vector u and vector v in Rn space are orthogonal to each other if inner product between vector u and vector v is equal to 0, right? So this definition is really important, so which will be used in today's lecture or our following lectures. So please remember this one. There was another theorem called the Pythagorean theorem, right? So as you can see here, if vector u and vector v are perpendicular, the length of the u plus v should be equal to length of the vector u plus length of the vector v, right? something like this. Okay, so this is the Pythagorean theorem. So yeah, there is another viewpoint of the inner product. So inner product between vector u and vector v can be represented by the vector length of the vector u and length of the vector v with the cosine theta, where the theta is the angle between the vector u and vector v, right? So it means that if the vector u and vector v is a unit vector, then this length should be 1, right? And then inner product vector u and vector v is only defined with the cosine theta. In other words, vector u and vector inner product vector u and vector v is defined with the theta, or between angle between two vectors, right? So it means that by analyzing the inner product between them, we can expect their relationship between their relationship in the vector space. Okay, so it was the inner product, right? And in the lecture 9.2, we introduced the orthogonal set, right? A set of the vector u1 through the up in Rn space is said to be the orthogonal set if each pair of the distinct vectors from the set is orthogonal. That is, if ui inner product uj is equal to 0 whenever I is not equal to j, right? So this is the definition of the orthogonal set, right? So here was the theorem. If the set S is an orthogonal set of the non-zero vectors in Rn space, then this set is linearly independent. Hence, it is a basis for the subspace spanned by S. So what was the definition of the linearly independent, right? What was that? So, okay, here was some kind of the weight term, something like this, right? So this is a linear combination of the vector u1 through the up, right? So linear independence means that this solution, the solution of this equation, only has a trivial solution, right? So when c1 through the cp is equal to 0, which is satisfied this equation only. So this is the definition of the linear independent. So in this case, we can represent any kind of vector in So in this case, subspace spanned by S is the linear combination of the vector u1 through the up, right? So okay, the subspace span u1, u2, up, right? So this is the subspace spanned by S, right? So in this case, the basis for this one, okay, let's say this subspace is W, right? So basis for the W is the U1 through the UP, right? So this is the theorem for the orthogonal set, right? So how can I prove this? Okay, we can represent this something like this, right? Because this is the where is that? Yeah, linear independent, right? So when we compute the inner product between this one and vector u1, it should be something like this. Finally, we get this one. So in this case, c1 is equal to 0, right? Similarly, c2 through the cp must be 0, right? So this set S is linearly independent. Okay, so in other words, if the U1 through the UP is orthogonal set, then this set is linearly independent. Okay. Then there's another definition. An orthogonal basis for the subspace W of Rn space is a basis for W that is orthogonal set. So in other words, let arbitrary set with the orthogonal basis for the subspace W of Rn. For each y in W space, the weight of the linear combination W is equal to C1 U vector U1 plus CP vector UP are given by the weight Cj is represented something like this, right? So let me draw some figure. So okay, this is the subspace W, right? And there is some kind of the orthogonal set, right? Let's say U1 through the UP, then one arbitrary point Y here, arbitrary point Y in W space can be represented by this one, linear combination of the basis term, right? Why? Because every point in the W space can be represented by the linear combination of the basis, right? Because this is the definition of the basis, right? So naturally, this vector y also can be represented by the linear combination of the u1 through the up, right? So in this case, what is the c1? C1. So in here, we can derive this term, right? So from here, we can derive the C1 is equal to y inner product u1 over u1 inner product u1, right? So this is the definition of this is a theorem for the arbitrary vector y with the orthogonal basis, right? So actually, what about this? Let's say there is another vector y here. Instead of in the W space, then how can we represent this vector with a basis, orthogonal basis? Actually, it's not possible, right? Because this vector y is not in the W space. But we want to approximately represent this vector y outside the subspace W. Then how can we approximately represent this W on the W subspace W? So how to represent this one approximately on the W? So this is related to the least square, so which will be discussed today's lecture. So in other words, this theorem will be extended to the general case in today's lecture. So let's see what it is. Anyway, please remember this theorem will be extended. Okay. Anyway, what was the orthogonal projection? If we have the vector y here, and we have another vector u here, and we want to find the y hat on the span of the vector u, right? So in this case, y hat is the orthogonal projection of the vector y, right? Then the question was how to find this alpha to find out the y hat, right? And here was the derivation that finally we found the alpha, something like this. So y hat is equal to y times u over u times u inner product u times u, right? So in this case, w hat, y hat So vector y hat is called the orthogonal projection of the y onto u, and this vector z here, right? y minus the y hat is called the component of the y orthogonal to u. Okay. So this is the concept of the orthogonal projection. Actually, this concept, this orthogonal projection was derived on the line here, right? Line of U. But today we will extend this concept onto the space or onto the subspace W. Then the question is how to find the orthogonal projection of the point Y onto the subspace W. So today we will discuss this. So it means that this term, this formulation is also related to today's lecture, so please remember this one again. And yeah, so it was the orthogonal projection on the line L. So today we will find out the new or another orthogonal projection on the subspace W, not a line, right? So yeah, right. So finally, what was the orthonormal set? What was the orthonormal set? So if a set S is called the orthonormal set if the set is a orthogonal set of the unit vectors, right? So this is the examples of the orthonormal set in Rn space, right? Right. So this is the orthonormal set. Finally, a matrix U of size m by m matrix has an orthonormal column if and only if the U transpose U is equal to 1 in a identity matrix, right? So how can you prove this? Something like this, right? So if you derive the U transpose U, something like this, then by definition, the shape of the output is the identity matrix, right? So finally we found the theorem, something like this. So which will be used in the our following lectures. So yeah, and there was one more theorem related to the orthonormal columns. So like this, you can easily prove this one, right? Here. So please try to derive this one yourself. Anyway, the properties A and C says that the linear mapping from X to the UX preserve the length and the orthogonality. Okay. So yeah, this is the end of the lecture 9.2. So yeah, today we will start the orthogonal projection on the subspace W or general case. Okay, let me start. So before starting, this is a final notification of our homework 2. This homework 2 was in the Blackboard from last week maybe. So please try to check this. If you are not started yet, please try to start as soon as possible. So here is the solution. Here is the problem set here. So yeah, please start as soon as possible. Okay, let me start. So orthogonal projection of the point in R2 space onto a line, which was discussed in the lecture. What was that? Lecture. Lecture 9.1. This one has the important analogy to the Rn space. So today we will extend those kinds of concept to Rn space or general case, right? So here's a very interesting observation. Given a vector y and subspace W in Rn space, so yeah, something like this. So let me draw the subspace W here and vector y here and zero vector say here because this is a subspace, right? And there is a vector y hat in W such that y is a unique vector, not unique vector, unique vector in W for which y minus y hat is orthogonal to W. So there is the y hat here, then y minus y hat, this is the y minus y hat, right? And y hat is up, and other vectors on the W space is orthogonal, right? So it means that W hat, there's a y hat. The y hat is the unique vector, and there is another. There are oh no, yeah, unique vector. Yeah, there's no other vectors, right? And another thing is that this this y hat is the unique vector in W close to the y. So in this case, this y hat is the closest to y. So distance between y and y hat is the smallest among the other distance between y and other vectors in W space. Okay, so this is a very important theorem, important observation. So today we will discuss how to find this y hat and what's the meaning of the y hat. Okay, so let me draw something like this. Okay, so these two properties of the y hat provide the finding the least square solution of the linear system, which will be taught in the section 6.5. So this one will be next week. So we will discuss this further, but today let me summarize what we have done so far and what is the least square solution of the linear system. Okay, so where are we now? So okay, so let me go back to the lecture 7.1, right? Here was some figure that represent the definition of the column space, right? So let me draw this one again. So in this linear algebra course, we are interested in to analyze and finding the solution of the matrix AX equals P, right? So in this case, the X is the some kind of matrix with the m by n. So vector X is the vector m by 1, right? And vector B is the n, right? And m by 1, right? So we are interested in this one. Then what is the solution set of this equation? If you remember this, the lecture 7.1, we can draw something like this. So this is the Rn space where the vector x is defined, and there is another Rm space, right? So A times vector x will be the B is equal to A times x, right? Right? So it means that if we have some value, some vector B here, that we want to find the x, right? So this is a solution of the Ax equals B, right? So here, right? So as you can see, the lecture 7.1, the possible solutions, the possible B here is called the column space. The column space, right, of matrix A, right? So if some vector B in the column space, then we can find the solution X, right? And then we already know if there is another vector C here outside the column space, there is no mapping point on the solution space X, right? Then we cannot find the solution. So it means that AX is equal to C is inconsistent, right? Or there's no solution, real solution, right? But in some case, we want to find the approximated solution of this one, because in real case, it is really hard to define. It is really hard to find the linear system that has the always has a solution. So in some case, we have to find the approximated solution of this inconsistent case, right? So then, what is the approximated solution in this case? What is the approximated solution in this case? Because the solution is only defined on here, right? Then it means that if we can find the nearest point on the column space, if we can find the nearest solution, this is the nearest point of C on W. W means the column space here, column space. Then by finding the mapping output X here, we can find the approximated solution of the C, right? So this is our strategy to find the approximated solution. So in this case, this approximation is called the orthogonal projection. Orthogonal projection. So actually, in last week's lecture, we introduced what was the orthogonal, right? So today we will use this kind of the concept to find the approximated solution, or approximated solution of AX equals C, right? So and then finding the vector X of the approximated solution of AX equals B is called the least square solution. Least square solution. So actually, this concept is really important, because in most cases we cannot find the real exact solution. So by introducing the least square solution, we can approximate the solution in case of that there's no solution of AX equals B or AX equals C, right? So today we will discuss how can we find this orthogonal projection, and how can we define this least square solution. But this least square solution will be discussed in the following lecture. So today we will just discuss this one, okay? So this is the general idea why we have to learn the orthogonal projections, okay? So if you see this one closely, the problem will be this is W, right? There is a Y, right? Y is equal to C here, right? Then this point will be the y hat, right? Then the question is how to find this y hat, so which will be the approximated of C on this W space, right? So we will talk about this one today, Okay. Okay, so let me start. So if a vector z, so before starting, let's introduce the orthogonal complement. So a vector z is orthogonal to every vector in subspace W of Rn space. Then z is said to be the orthogonal to W. Okay, so first of all, if there is a space W like this, and there is the another vector z here, and let's say this z vector, this z is the orthogonal to every vector in subspace W, then z is said to be the orthogonal to W, something like this, right? And the set of the all vector z that is orthogonal to W is called the orthogonal complement. Orthogonal complement of W, so which is denoted by perpendicular W, something like this. So whole possible z, the set of the whole possible z is denoted by W perpendicular, right? So vector x is in the W perpendicular if and only if the x is orthogonal to every vector in the set that span W, and set W perpendicular is subspace of Rn space. So to prove this definition, we need some kind of the technique, but today we will not discuss this one, but we can use this property to derive the following definition. This one will be derived by homework in homework 3. So let's think about in homework 3. But today we'll just use this concept to derive our other property. Okay. Okay. So here is the theorem called orthogonal decomposition theorem. Orthogonal decomposition theorem. Okay. Okay. Let's start. So let W be the subspace of the Rn space, then each y, vector y in Rn space can be written uniquely in the form y is equal to y hat plus z, where y hat is in W and z in W perpendicular W. So let me draw a figure again here. So let me say there is the vector subspace W here, right? Yeah, there is the zero vector here because this is a subspace, right? And there is a vector y here. Then each vector y in Rn space can be written uniquely in the form of y hat plus z. Y hat here. And where's that? Yeah. Z here. So in this case, y is equal to y hat plus z, something like this. So this y can be uniquely written uniquely in the form of y is equal to y hat plus z. Okay, so this is the orthogonal decomposition theorem. So in fact, if the y set y1 through the yp is any orthogonal basis of the W, if there is the orthogonal basis of W, then this y hat is going to be something like this. Y inner product u1 over u1 inner product u1 times u1 plus y inner product up over up inner product up times up. Okay, so in other words, if we have the vector u here and the orthogonal basis of the w, then we can find out the y hat with this equation, right? So, and then this w is the y minus y hat because of this one, right? So in other words, okay, so if we have the orthogonal basis of the space W and we have the arbitrary vector y, then we can represent, we can find out the y hat in terms of the y and u1 through the up, right? And then z, the orthogonal complement z is equal to y minus y hat, right? So this is the orthogonal decomposition theorem, right? So if you go back to our lecture 9.2, there was the similar theorem, right? So if you remember this one, right? In this case, each y in W space, then y can be represented with u1, up, and y, right? So comparing to this one, if we go back to our lecture 10 here, this equation is almost the same to this one. Instead of there, except for there is the y in the lecture 9.2, y here, but the difference between lecture 9.2 and today's lecture is the y can be the any kind of the vector in the Rn space. So this y cannot be no longer in the subspace W. So y can be the any kind of vector. So this is the way to find out the y hat, right? And let's prove this theorem. So before starting, the vector y hat is called the orthogonal projection of y onto the w. So this is y and this is w, and y hat is represent projection of y onto w, something like this. Orthogonal projection of y onto w, which is written as something like this, right? So if you remember this one, there is the only single representation of the y hat. In other words, y hat is unique, right? So this is the orthogonal projection of y onto w. And this one can be represented by this one, right? So let's find out, let's derive or let's prove this one. So first of all, let the set u1 through the up be the any orthogonal basis for w and orthogonal basis, and define y hat by 2. Okay. Here this is the equation 2, this is equation 1. Okay, so we can represent y hat something like this, right? And then y hat is in w because the y hat is a linear combination of the basis of the u1 through the up here. So as you can see here, y hat in the subspace W, right? Okay, and then let's say z is equal to y minus y hat by definition, right? And then since u1 is orthogonal to other remaining vector, such as the u1 through the up, so what I want to do is to find out z inner product u1, right? So because the z is equal to y minus y hat, so when we derive this one, y inner product u1 minus this term, because the y hat was something like this, right? So if you compute this term separately, this is first term, and remaining term will be 0. Why? Because u1 inner product uj, where when j is not equal to 1 is equal to 0. Okay, and then y inner product u1 minus where is that? So y is here, right? Y is here, and this term, and where is there is error, right? There is no u1 because u1 is here, right? So in this case, this term is eliminated by this term, right? So there is only term here, right? Because this one is this one and this one is same, so this one is going to be 0, right? So it means that vector 0 and vector u1 is orthogonal each other, or z is orthogonal to u1, right? Similarly, z is orthogonal to each uj in the basis for w by using the similar verification, right? So hence z is orthogonal to every vectors in w. Why? Because every vectors in w can be represented by the linear combination of the vector basis vector, right? Because this is the definition of the basis. Then z times this one is equal to 0, right? So because this one, right? Z is orthogonal to each u1, u2, and up, right? So we can say that Z is orthogonal to the every vectors in W space, and that is the Z is in the W perpendicular space, right? So if you remember this one, if you remember this property, this Z is in the W perpendicular, right? And then what should we do? We have to show that the decomposition in 1, this decomposition is unique. So we have to derive this one is unique. So to show the decomposition in 1 is unique, suppose y also can be written as the y is equal to y1 hat plus z1. So in W and W perpendicular space, and y hat plus z is equal to y1 hat plus z1, since both sides equals to y. So we can represent something like this. So y hat minus y hat 1 is equal to z1 minus z, right? And this equality show that the vector v is this one, right? Y hat minus y hat 1 is in W space and W perpendicular space, because the Z1 and Z are both in W hat space, and W hat is the subspace, right? So this one and this one is the W perpendicular W space. So y minus y hat is in W and W perpendicular space, right? So which vector satisfy this one? Which vector V satisfy this? Which one? So, in other words, vector V should be also should be in W and W perpendicular space. So this is the W and this is the W perpendicular, and which one satisfy this? When V is equal to 0, right? When V is equal to 0. So in other words, the only 0 vector satisfy this statement. Okay? So in this case, we can represent y hat minus y hat 1 is equal to 0, right? So it means that y hat is equal to y1 hat, y hat 1, and also z1 is equal to z. Okay? So in other words, there is the only unique representation of the y hat and z. Okay, so this is the proof of the orthogonal decomposition theorem. Okay, so let's see the examples of the orthogonal decomposition theorem from now on.